This is the Chem 1 lecture on voltaic cells. Devices that use redox reactions to produce or use electricity are called electrochemical cells. And then there's a couple of different types of electrochemical cells that we're going to talk about. If the reaction produces electricity, it's called a voltaic cell or battery. We're going to spend the majority of today talking about that. If the device uses electricity, they're called an electrolytic cell. So an example of a voltaic cell is a battery, which is in a lot of different things, like your cell phone. If you watch the TED Ed video that's on our website, it talks about rechargeable batteries and how batteries work, but they are producing electricity from the reaction. An example of an electrolytic cell or process is electroplating, like sometimes costume jewelry gets electroplated with gold, and so that's using electricity to kind of force a redox reaction and plate something. We're going to focus on voltaic cells for this lesson, which is going to be a spontaneous redox reaction. And so in your notes there's an example with zinc placed in copper 2-sulfate solution producing solid copper and zinc sulfate. We want to write the two half reactions, and so to do that we have to figure out who's being oxidized, who's being reduced. Elements that are not in a bond have an oxidation state of 0. In the word they already told us copper was +2. Zinc in a bond is +2, and so we see it looks like zinc is oxidized because it's becoming more positive. And copper ions are being reduced back down to copper. So zinc must have lost 2 electrons, and the copper ions must have gained those 2 electrons. And then to determine E, you need a voltage or potential chart. So remember, it's a reduction chart, and so we can look up copper +2 going to copper is 0.340. Zinc, remember, for oxidation, you simply flip the charge. So on your sheet, it's negative, but we'll flip it to positive 0.763. Add up your total voltage. So the current we would expect from this reaction would be 1.103 volts. If this redox reaction is to be used as a source of electrical energy, the two half reactions must be physically separated. When the two half cells are separated, electrons can be made to flow through an external circuit producing an electrical current. And we'll dive into what do we mean by putting them into half reaction cells. All right, guys, I'm going to go through the different parts of a voltaic cell. The definitions are on the front page of your notes. This diagram is on the back page of your notes. So first part is you're going to see two half cells, and these separate the oxidation reaction from the reduction reaction. You have a salt bridge that we will talk about. This is going to send ions into each half cell depending on what is needed. So if one cell is starting to become more positive, they're going to send in negative ions from the salt bridge to help neutralize the solution. And then if we're starting to have a negative charge build up, they're going to send positive ions in to balance out the charges. So the half cell that has oxidation happening is called the anode. So in our example of zinc being oxidized, zinc is losing electrons. That would happen at the anode. And a way for y'all to help remember that oxidation happens at the anode is this awesome picture of an ox. Anox. Oxidation happens at the anode. And so the electrons are being lost from the solid zinc. The electrons are being lost, and they're going to be carried through an electrical wire, and they're going to move towards the half cell with reduction. The cell where reduction's happening, where the gaining of electrons happening, is called the cathode. And so a way for y'all to remember that is red cat, hence the picture of the red cat. So reduction happens at the cathode. And here your ions are going to absorb the electrons or gain the electrons and actually become that metal. And so you'll actually see the cathode get bigger. And so sometimes you'll hear us say fat cat, is that the cathode gets bigger because you're producing metal, like you're making solid copper. And you're going to see the anode get a little skinnier because that solid zinc is becoming zinc ions as it loses electrons. Okay, so I think I hit most of the definitions. We have two half cells, one for oxidation called the anode, one for reduction called the cathode. An electrode are the actual pieces of metal that are helping conduct the electricity. You have a salt bridge that is helping prevent the charge buildup, so it's helping keep the charges balanced. You have a voltmeter that's able to read the current that is happening through this redox reaction. And we'll get into another example. Something that you're always going to see in a redox reaction is you're always going to see the electrons flowing from the anode to the cathode. And if we remember that at the anode, oxidation occurs at the anode. Well, oxidation, let's do lots of acronyms, oil rig, oxidation is the loss of electrons. You're always going to see the electrons leaving the anode going towards the cathode. And so we don't want you to use terms of like the electrons move right or they move left, because it just depends on where the anode is and where the cathode is. So another acronym, fat cat, electrons flow from the anode to the cathode. I also like that it's alphabetical, A to C, anode to cathode. So once again, we'll kind of recap what's happening in a battery or in a voltaic cell. So oxidation happened in our example when zinc loses 2 electrons. So here we had a solid piece of zinc, so we're reading it from left to right, and the zinc lost electrons. And when it did, it produced zinc ions. So we will continue to see a production of zinc ions. So the concentration or the amount of zinc ions will continue to increase in this redox reaction. But the amount of zinc is going to start to decrease. What happens to the size of the anode? This anode is literally going to start to kind of shrivel away because that solid zinc is now falling into solution as zinc ions as the electrons are moving from the anode to the cathode. What's happening at the cathode? Red cat. So reduction happens at the cathode, and so here in the half cell there's a solution with copper plus 2 ions. Those copper plus 2 ions are gaining electrons that are coming from the anode and literally are turning into solid copper. So you're going to see the size of the cathode always increase. So that's where I sometimes think about fat cat too, is that the cathode is the one that gets bigger because you're producing a metal. And so then the copper plus 2 ions will be decreasing because those are the ions that are becoming the metal at the cathode. And then last part is the salt bridge. What's the impact of the salt bridge? Well, if we're starting to produce zinc positive 2 ions, we're going to have a buildup of positive charge unless a salt bridge can come in and bring a negative charge to help balance the positive negative charges. And then over in the cathode, we're losing plus 2 ions. They're becoming solid. And so we're going to start having a negative buildup of the sulfate ions. So our salt bridge will flow in positive ions to help balance the negative charge. Because if charge builds up at either of the electrodes, the battery is going to stop. Last thing is the labeled charge of the anode and the cathode. The anode gets the negative charge because there is a loss of electrons happening, and the cathode gets a positive charge because there is a gain of the electrons happening. So here's a zoomed in picture of what's going on in the anode and the cathode. So here at the anode, there's a loss of electrons. So there's solid zinc, the electrons are being lost, and so that zinc solid becomes an ion. So you see a production of zinc ions, zinc positive ions, happening in the anode. The electrons always travel from the anode to the cathode. and then those electrons are coming in. Those copper 2 ions are able to gain those electrons and then attach to the electrode as solid copper. Okay, we're going to work through one example from start to end, and this is just going to take practice. So you guys have practice in your notes. You'll have a practice day tomorrow. So every problem we give you, we're always going to give you 2 metals, 2 electrolyte solutions, and what the substance will be in the salt bridge. And so my recommendation is to always write the 2 reduction reactions. So you have aluminum plus 3, and you have solid aluminum, so that's showing reduction. And I'm going to do the same thing. We have Pb plus 2 going down to lead. And I want you to go use your standard reduction potential sheet and write in the voltage associated with both of these. So aluminum gaining 3 electrons would have a voltage of negative 1.676. And then lead 2 ions being reduced to lead would be negative 0.125. Now notice in this problem we haven't told you which one's being reduced, which one's being oxidized. This is where it's really different than 17b, where that was already chosen for you. We are making a battery, and a battery needs to be spontaneous. We need to be producing electricity. And so our cell potential always needs to come out positive. And so for 17C only, you get to choose which metal should be oxidized, which one should be reduced. And so if you write down both of your E's, flip the most negative one, because you ultimately want your E to come out positive. And so because aluminum is so negative, it really doesn't like to be reduced, then let's have aluminum be oxidized. So I'm going to rewrite this as aluminum being oxidized, and now my value is 1.676 plus my negative 0.125, and so my potential for this battery would be positive 1.551 volts. So when we do this redox reaction with aluminum being oxidized and lead being reduced, we're going to produce electricity, which is what we want. We want our battery to work, to give us energy. So that's, I think, kind of the trickiest part about setting up the battery, is the fact that you're going to have to decide which one's better at being oxidized, which one's better at being reduced. Remember, anytime you have a voltage that's negative, they're not easily reduced. So that's probably going to be the one that you want to flip. But you flipped it right if your battery is positive. So now I'm going to rewrite things a little more neatly. So we decided that aluminum is best oxidized and lead 2 ions are going to be reduced. You are able to choose which half cell you want to put them in. I just put aluminum in the first one, but you could have absolutely used the right half cell for the oxidation. So I'm just going to give myself reminders. Aluminum's being oxidized. Lead 2 ions are being reduced. I know that where oxidation happens, that's called the anode, the negative charge. Where reduction happens is called the cathode, red cat. And I'm just going to fill in, okay, I know this electrode, this piece of metal is aluminum, and our other electrode is going to be our other metal, which is lead. We know that both of these half cells are in solution, which is going to have aluminum ions as well as nitrate ions. And where I got that from is that they gave us a 1 molar solution of aluminum nitrate. And then in our cathode, we had lead 2 nitrate, so we're going to have lead 2 ions as well as nitrate ions. And then our salt bridge is going to have sodium nitrate, and I'm just going to go ahead and dissolve the salt into its ions, and then I'm just going to run this reaction. So it starts with the anode when there's a loss of electrons. So we're going to see the electrons always flow from the anode to the cathode. When aluminum loses electrons, it will produce aluminum plus 3 ions. So this solution will start building up with aluminum plus 3 ions, which are all positive. So the salt bridge is going to have to send in some negative ions to help balance out that positive charge so we don't have a buildup. As the electrons move through the wire and down through the electrode, the lead 2 ions are going to gain those electrons and literally become lead. So we're going to see the cathode electrode literally grow in size. The positive ions are going out of solution because they're turning into lead, and so there's going to be negative ions still there. So the salt bridge is going to have to send in positive ions to balance the positive negative charges. We don't want one charge over the other. Like, we don't want a majority buildup. We want them to be even or neutral. And then, I think we got electricity. And we've already predicted that I think it would be 1.551 volts would be the current that could be flowing through this battery. So now they're going to ask us questions about the drawing that we just did. So which is more easily oxidized, aluminum or lead? Well, we learned that aluminum is more easily oxidized. That's the charge that we flipped. Write the balanced equation showing the spontaneous reaction. I'm going to come back to that one. We figured out the maximum voltage by adding up our two cell potentials. We got 1.551. The direction of electron flow, so it always moves from the anode to the cathode, but we're going to be specific. We knew our anode was aluminum, our cathode was lead, so it flowed from aluminum to lead. What is the direction of the positive ion flow? So in our picture, in our last screen, we said that the positive ions are going to flow into the cathode to help balance out the charges. And so they're literally flowing into that lead to nitrate solution. Okay, so going back to the two half reactions, and we're combining an overall. If you remember back in 17b, when you take your two half reactions and combine, you have to make sure the electrons are the same, because that's how redox works. If 3 electrons are lost, then 3 must be gained. But it's saying 2 is gained, and so you end up having to find your least common denominator. So between 3 and 2, we can get the electrons to be 6. So I'm going to multiply my whole oxidation reaction by 2 and my whole redox reaction by 3, so that I have 6 electrons lost, 6 electrons gained. And you know you've done your balanced equation right when your electrons cancel. And then you simply just add up everything that's on the reactant side and then everything that's on the product side. So we know our reactants are solid aluminum and lead 2 ions. And we know our products are aluminum ions and solid lead. But then you have to account for our multipliers. So everything with aluminum got multiplied by 2. Everything with lead got multiplied by 3. Another way to check yourself that you've done it right is you should have equal amounts of actual elements, like 2 aluminums, 3 leads, 3 leads, but then your overall charge should be the same. So aluminum is 0, 3 times 2, so this whole thing has a positive 6 charge. 2 times 3, the whole product side has a positive 6 charge. This is 0, so the sides are also balanced in charge. Okay, last question is talking about the battery. Which electrode is decreasing in size? It's always going to be your anode, because it's the one that's losing electrons. And so our anode in this example was, or has been, aluminum. Which electrode is increasing in size? It will always be your cathode, which in our example was lead. What's happening to the concentration of aluminum ions? They're increasing as they fall off the electrode once those electrons have been lost. So remember, we started with solid aluminum, and then literally we're producing aluminum ions as electrons are lost. What's happening to the concentration of lead ions? Those lead-2 ions are decreasing because they're literally becoming lead. What is the voltage in the cell when this reaction has reached equilibrium? When it's reached equilibrium, the voltage just becomes zero. There's no longer a difference in potential, and so the battery will be dead at that point. Which is the anode? So anode, we say anox, so oxidation, and so aluminum was our anode. Our cathode, red cat, the actual electrode was lead. What is the positive electrode? Ooh, I like the T, can also mean a positive. So your positive electrode is always your cathode, so also lead. And then your negative electrode, ooh, and then anode has the N for negative, I like it, would be aluminum. So these are the types of questions you would expect to be asked. We'll always give you a blank battery for you to draw all over it and kind of picture what's going on. But practice, practice, practice. Hope you've gotten something out of this, and good luck.